Hello, my name is Justin Kasowski. Today I'll be presenting our research on immersive virtual reality simulations of bionic vision. Bionic vision, in a nutshell, refers to electronic devices that are implanted in order to restore vision in those who have lost their vision. These devices typically consist of a head-mounted camera and have an extremely limited field of view. This means that prosthesis users must turn their head in order to update what their camera is seeing. Now, virtual reality emulates this in a highly effective way, since the virtual scene is also updated based off movements of a head-mounted device. For this, we wanted to use a neuroanatomically inspired model for our prosthetic vision, and the basis of that is shown in the upper right here. This is representing a retina, which has neuronal cells that send their axonal projections through the optic disc and eventually to the brain along these nice arch-like pathways. So you can imagine if you're trying to stimulate a single electrode, such as the one highlighted in red here, yes, you will hit the neurons that are immediately under that electrode, which are representative of that space in the visual field. But you're also going to hit neurons that are just sending their axons past that point in space. And so we believe the perception that this would cause is kind of like what is shown on the bottom here, essentially just kind of a distorted blob that is smeared out along those axonal pathways. We quantified this with two parameters, rho and lambda. Rho just representing radial decay away from the electrode, and then lambda, which would represent the decay along those axon pathways. We had two overarching questions we wanted to answer. First, we wanted to know if immersive technologies, specifically VR headsets, matter. A lot of the previous simulated prosthetic vision research has just used computer monitors, and it hasn't been systematically evaluated if switching to a VR headset would affect performance. Second, we want to know if those neuroanatomically inspired distortions matter. And so similarly, a lot of the previous research has just used a simplified model, mostly just representing each electrode with a focal spot of light. And we wanted to see if there was an effect in adding those distortions. To answer these questions, we created virtual versions of two tasks. On the left here is just a very simple letter recognition task. And on the right is a hallway navigation task in which real prostheses users were tasked with reaching the end of the hallway while avoiding collisions. First task looked a little bit like this. Participants are presented with a letter on a virtual laptop screen. The image is processed into what we believe prosthetic vision looks like, and the result is shown on the bottom here. So we simulated three different devices. This left block here is a 6x10 electrode array, and that is representative of the real device that was used in the real life versions of this task. And then that middle block and that right block there are what we believe future devices with an increased electrode count, therefore an increased field of view, but using that same configuration, what those may look like. Among each of these blocks, as you move from left to right, you have an increasing value of lambda, and that's just increasing the amount of distortion along those axonal trajectories. And then as you move from top to bottom, you are increasing rho, and that's just going to increase the radial distortion away from each electrode. So the first question we asked is if the number of electrodes affects performance. And we used two metrics for this. First, F1 score, and second, time. F1 score is just a modified accuracy score. So higher values are better performance. And then conversely, lower time was perceived as better performance. And we would argue that, yes, increasing the number of electrodes did seem to increase performance across both versions of this task. Second, we want to know if radial distortions matter, and they did somewhat. So it did reach significance across a couple of the conditions, but the majority didn't really see much benefit to those lower levels of distortion. Third, we want to know if distortions along the axon affected performance. And for this, we got a resounding yes. So you can see this figure on the left here. When those lambda values or that axonal distortion was really low, participants were scoring next to perfect. And then as you increase that to the maximum distortion values, they were essentially performing down at chance levels. Lastly, we wanted to know if VR headsets mattered, and it did across the majority of conditions, but it did not reach significance in all conditions. The second task looked a little bit like this. Participants were placed either in front of a monitor or between two ropes, which represented the edges of the hallway, and they were tasked with reaching the end of the hallway without running into any of the simulated people. Now, both of our tasks have a video component, which is just readily available on the GitHub for the project, if you'd like to see kind of the task in action. Now, we did use the same block conditions, and those are shown on the bottom here. And we asked the same questions. So first, we wanted to know if the number of electrodes affected performance. And there was a slight time benefit in the monitor version of the task. But overall, it didn't seem like too much of a benefit. Second, we wanted to know how that radial distortion affected performance. And again, there was a slight time benefit in the monitor task, but overall, it did not seem to matter. Third, we want to know about those axonal trajectories and the distortions. And for this, we did reach significance when comparing the lowest levels of distortion to either of the other two levels of distortion, at least for the HMD version of the task. And then the last question we had was if there was a difference between a standard computer monitor and an HMD. And for this, we got highly significant differences across all different conditions when comparing the light gray, which is the HMD, to the dark gray, which is the monitor. In summary, we found that performance was consistently better for the HMD versions of both tasks, and that effect was even more pronounced for the navigation task. Secondly, we found that those previously ignored distortions, which are caused by the neuroanatomy, they do matter. There was a drastic effect on performance in the letter recognition task, and there were significant effects in the HMD version of the navigation task. And with this, the overall goal is really creating a useful model of prosthetic vision. And doing this, we believe we'll be able to provide a more realistic estimate of current technologies, use more realistic simulations to assess advanced stimulation strategies, and then hopefully guide the development of future devices. And all of these goals, the overarching goal is to increase the quality of life for those with retinal degenerative diseases. That's it. I'd like to thank Augmented Humans for having me. If you have any questions, please feel free to reach out to me either at the conference or through my email.